This is going to pick up where yesterday's review session left off. And yesterday we went through questions 1 through 11 of the practice test. Today we'll pick up with question number 12. In this question, in the circuit shown, are the following quantities the same or different? So we've got a battery here. That's a 12-volt battery. I can label this on the picture if I wish. I've got 3 resistors. They're all 5 ohms. And my questions are asking about, are the currents and the potentials the same or different? So, 2 ideas I have to get in my mind first are things in series, or things that are all in a row, and things in series have the same current. The other thing I know is that things connected in potential, and those are connected tops to tops and bottoms to bottoms, those things, my goodness, things that are connected in parallel, I'm giving myself away here. Things are connected in parallel, top to top and bottom to bottom. Those things have the same potential. So it's like this end of the resistor comes out and gets hooked up to the battery, and then this piece of wire comes out and gets hooked up to the battery. So this branch is in parallel with this branch. So this branch and this branch are in parallel. Overall, those two would have the same potential. These two, R2 and 3, they're the only 2 things in a row. So R2 and 3 are in series. So we're going to think about each of these different items and try and answer our questions. The other thing we'll remember as we go through is Ohm's law, which states that the potential across something, V, is equal to the current through it times its resistance, R. So there's our key concepts. Now let's start working on it. So the currents through resistors 1 and 2. Let's make sure we understand what's happening to the current. Some current comes out of the battery. It comes to this point in the circuit. Some of it is going to come down here. Some of it is going to come over and come down through here. So the question is asking, is this current right here the same as this current right here? Let's try and figure that out. We can sort out what current is if we use Ohm's law. This branch is going to be pretty easy. This battery is in parallel with this resistor is in parallel with this battery, so we can use it. We can figure out what the current through here is. This branch is in parallel with the battery, so we know the whole potential, but the 2 resistors are in series. So let's simplify a little bit first before we start to answer our question. So I'm going to say we're going to simplify, and the way we're going to simplify is by dealing with our 2 resistors, which are in series. If 2 resistors are in series, we know that the equivalent resistance is going to be the sum of the 2 resistances. So the equivalent resistance in this branch is R2 plus R3, which is 5 ohms plus 5 ohms equals 10 ohms. Let's redraw this circuit. So we'll have our battery, that's our 12-volt battery. We've got our resistor, R1, that's 5 ohms. And then this branch, we take out R2 and R3, and we put in the equivalent resistance of 10 ohms. The currents don't change. The battery puts out a certain amount of current. We have a certain current through R1, and we have a certain current through this R equivalent. Whatever current flows through this R equivalent is the same as the current flowing through R2 and R3 because those are in series and series has the same current. Okay, so we've got that sorted out. We know that R1 and R equivalent are in parallel with the battery, so R1 has a potential of 12 volts and R equivalent has a potential of 12 volts. Let's use that to find the current flowing through those batteries. So we know that V equals IR, so I is equal to V divided by R. 12 volts divided by 5 ohms. 12 volts divided by 5 ohms gives 2.4 amps. So the current through this branch is 2.4 amps. Okay, what about this branch? V equals IR, I equals V over R. The potential is 12 volts because it's connected in parallel with the battery. The resistance is 10 ohms. 12 divided by 10 is 1.2 amps. So 2.4 amps goes through this resistor. 2.4 amps goes through both of these resistors. Oops, sorry. 1.2 amps goes through both of these resistors. Okay, now we can answer this question. Are the current through resistors R1 and R2 the same or different? They're different. So the answer to this one is different. That was choice number 2. All right, the current through resistors R2 and R3, well, they're in series, so it has to be the same. The potential across resistors R1 and R2. Okay, we can definitely find the potential now. We know that potential is current times resistance. So for each of those, we can find the potential. So for this one, V equals I times R, 2.4 amps times 5 ohms equals 12 volts. We kind of knew that anyway because R1 is in parallel with the battery. What about the potential across R2? So the potential is the current, 1.2 amps, times the resistance, 5 ohms. 1.2 times 5 ohms is going to give us 6 volts. So to answer our question here, the potential across resistors R1 and R2, 12 volts and 6 volts, those are different. How about the potential across R2 and R3? Well, our potential across R3, I don't have much room here, I'll try and squeeze it in. Potential is equal to I times R, 1.2 amps times 5 ohms equals 6 volts. So the potential across both of these, because they have the same current and the same resistance, they're going to have exactly the same potential. So those are the same. So there's our answer to question 12. Now we can move on to question 13. Question 13, we sort of got started on this one in question 12, but we'll start over here just to make it nice and neat and complete. What is the equivalent resistance for the circuit shown in ohms? So let's get started on our circuit. When we do these equivalent circuits, we generally start at the outside, so we go to the end furthest away from the battery and work our way in closer to the battery. As we go, we look for obvious connections. My first obvious connection I see is that R2 and R3 are in series. We already dealt with that a moment ago, but let's do it again. There's our battery V, there's our resistor R1, here are our resistors R2 and R3, and there's our battery. So these two are in series. Our series equivalent is when you just straight up add the resistors together. That's 5 ohms plus 5 ohms to give us 10 ohms. Our next step is to take out these two resistors and put in the equivalent resistance. So we've still got our R1, we've still got our battery V, and now we've got our equivalent, which is 10 ohms. If we look at these two, we see that these are connected by their tops, connected by their bottoms. These are in parallel. When we add resistors in parallel, we know that 1 over R equivalent is 1 over the first resistor, R1, plus 1 over the second resistor. Okay, I'm going to go back in time now and call this R equivalent for that series connection. I'll put an S on it. So that's 1 over 5 ohms plus 1 over 10 ohms. If you're a numbers kind of person, you're probably going to do that on your calculator. I'm more of a fractions kind of person. That's 1 over 5 is the same as 2 over 10 plus 1 over 10 equals 3 over 10 ohms. Then to get our R equivalent, we have to take the reciprocal, which is 10 ohms divided by 3, or 3.33 ohms. We draw our circuit once more, And this is the kind of diagrams you'd have to show on an exam. So you would have to show these step-by-step diagrams and calculations. You finish with your R equivalent, which is 3.33 ohms, and the potential of your battery right here. After this step, you could be asked other questions such as find the current running through this circuit. You would use your 12 ohms and your 12 volts and your 3.33 ohms and your Ohm's law, V equals IR, to find the current. That would give you the current going through this branch. Once you know the current going through this branch, you could find the potential across this branch. It would be 12 volts. Because this is a parallel equivalent of these two, both of these would have a potential of 12 volts, so you could find the current through both of these. Then you could work backwards. You know the current through this one, you could find the potential. You know the current through these, you could find those potentials. So those are the sorts of things you would do with these equivalent circuits. Okay, our next question we'll look at we'd like to consider a charged object of +2 coulombs, and it's in a constant electric field pointing in the forward x direction or to the right. I'm going to put my coordinate system on here. Plus x is to the right, plus y is up. By how much does the electric potential, this is our voltage V, decrease for a displacement of 0.1 meters in the forward x direction? So we start here, go 0.1 meters forwards, and then we go 0.2 meters upwards in the y direction. We're given some choices here. It was a multiple choice question when we gave this exam. So let's think and let's make sure we understand what's happening here. Our electric field is 5,000 newtons per coulomb in the x direction. To write our electric field as a vector, we would say that E is 5,000 newtons per coulomb in the x direction. That tells us that this part, this is the x component. The electric field only has an x component. What that tells us is that the y component is equal to 0. This is going to be really important as we figure out potential. Let's think about our motion happening in two steps. Let's say first it goes to the right. Let's see how much the potential changes there. And then it goes up. Let's see how much the potential changes there. We'll add those together to get the total potential. So what is delta V as it moves over distance delta x? We have to remember our relationship here, that our x component of electric field is negative delta V divided by delta x. That tells us that delta V is negative the x component of electric field times delta x. So we've got minus 5,000 newtons per coulomb times 0.10 meters to give us minus 500 volts. Okay, so that's how much the electric potential changes as we go from here to here. It decreases by 500 volts. That's what the negative sign means. Now let's see how much does it change as we go in the positive y direction. You might know this without doing any calculations, but bear with me. Delta V over delta y. Well, EY equals minus delta V divided by delta y. That means delta V is minus EY, delta y equals minus 0 times 0.2 meters equals 0. When we move perpendicular to an electric field, there's no change in potential. So you can move as far as you want in the y direction and you will never get a change in potential. So the total change in potential, delta V, is minus 500 volts, and our answer is it decreases by 500 volts. Next question. So this is a true-false multiple choice type question. This isn't really something we would give you on a current in-person kind of an exam, but it's worth it just to discuss each of the ideas. Consider a negatively charged object in a constant electric field. Say it's inside a parallel plate capacitor. Pick which of these things are true. So if you're trying to draw a picture of what's happening, a capacitor means we have two plates. We know the electric field goes from the positive to the negative. So we could draw that electric field if we want. There's our positive plate, there's our negative plate. The electric force on the object is parallel to the equipotential lines, but in the opposite direction. Okay, so here's our electric field. Here's our negative charge. It's talking about electric force. Let's draw the electric force. We know electric force is equal to charge times electric field. If our charge is negative, the field and the force are in opposite directions. So there's our electric force. So our electric force is to the left, our electric field is to the right, but this question asks about the equipotential lines. What we know about equipotential lines, and we drew these in one of our lectures, is that they're always perpendicular to the electric field lines. So these are the equipotential lines. So now let's read the full question. The electric force is parallel to the equipotential lines. That's already not true because it's perpendicular, but in the opposite direction. This one is false. We'll call that an F for false. Next option, the electric field lines are perpendicular to the equipotential lines. That one is always true for any electric field and its set of equipotential lines. Electric field lines move towards lower electric potential. That is always true. You can see that in our equation. You remember we wrote on the previous slide, Ex is minus delta V over delta X. This minus sign is what tells us that electric field points towards low potential. So this one is also true. The object will move towards higher electric potential energy, but lower electric potential. Now this one is false because whenever we release a charge from rest in an electric field, it will always move towards lower potential energy. That's what objects in the universe do. If you let them go, they always go towards lower potential energy. Think about a car on a hill or a car halfway up a hill. If you let go of the car, it's going to roll downhill towards low gravitational potential energy. It won't go up the hill by itself. Same thing is true for charges in electric fields. They'll go towards low potential energy. They won't move towards high potential energy. Okay then, our next question starts its own section, so why don't we start with a new video for that one.